Hello, welcome back everybody to yet another exciting session of Bang Bang Con. My name's Sarah, I'm one of the organizers.
And hi, I am Dev. I'm one of the other organizers.
And tonight we're going to bring you four more wonderful sessions. We're on session number 8, and tomorrow is our last day. It's been a wonderful week so far, and I've been enjoying everything I think I've seen all week long. This is Theodosius, by the way. What about you, Dev? What have you? How's the week been for you?
Oh, if you're like me on the West Coast, this is just after workday on the Friday. It's the perfect thing to watch at this time. It's chill, lo-fi time to study slash relax to, really.
Yeah.
I'm really looking forward to today's talk.
And if you were live, you saw the 5-minute countdown with the dancing dinosaurs. The sync watch, I think we usually cut that off. But I was kind of wondering if after all that time of all that dancing, if you got dinosaur from all of it. Never mind. Never mind. Would you like to talk about sponsors or would you like me to talk about sponsors?
I think you can talk about sponsors.
Okay. We have lots of lovely sponsors that have helped us make a great, wonderful, and accessible conference. Theodosius, come on, man. If Cindy could bring up that slide. So they help provide money to make this a wonderful conference. We pay all of our speakers, keynotes, and the lightning talks. We provide live captioning. We have wonderful AV people. Just so many great things are able to happen. Even when it's remote, it still costs a lot of money. So wonderful sponsors like Xander, Daily, Wherewithal, Phase Row, Full Story, Mapbox, Two Sigma, Discourse, and Accelerated Tech have all contributed some funds to help make Bang Bang Con 2021 possible. So please thank all of them on Twitter or, wander by their websites if you can do that. All of them have links on their websites. I think some of them have like referral links that you came from Bang Bang Con. So yeah.
And don't forget to tweet about this conference. It will help us reach more people, and you know how wonderful it is. So if you tweet, make sure to include the official Twitter account at BangBangCon, and please use the hashtag #VirtualBangBangCon because as featured today in Business Insider, we had a naming collision with BTS, and we love BTS, but we want people to be able to look up things related to this conference with a handy hashtag. So please use hashtag #VirtualBangBangCon.
And you can also tag us, the conference, at Bang Bang Con as well. So I believe has there been a highlight for you, Dev, over the past week that you just enjoyed?
I think Bang Bang Con has been the highlight of the past week for me. Just I missed a few of the initial talks. I have been catching up on them, and all of them have been so wonderful this year. It really brings out joy and excitement and surprise of computing.
Yeah. And all week long, we've also had hallway tracks after our sessions. So it's been lots of fun being able to hang out with people and chat with them about all sorts of things. I think we've seen conversations about the talks themselves. We've seen everything from cheese plates to all sorts of other things, people hacking servers, and I don't know. It's been a lot of fun. So I've appreciated that. We could probably go ahead and wander into our first talk. So our first talk of the evening or afternoon or morning, whatever time it is for you, is called Dithers of the Error Diffusion Kind. It's by Daniel Timken. And Daniel Timken is an artist and a writer who is skeptical that human beings can understand logic or really writing working code at all. They created the fat finger dialect of JavaScript, which allows you to run typo-ridden JS, and the entropy language, where all the data decays the longer your program runs. You sound delightful. They also designed dither patterns for an alternate computer history where our screens are hexagonal, triangular, or other shapes. So here's Daniel with our first talk.
Hi, I'm Daniel Tumpkin. I'm an artist and programmer, perhaps best known for my blog Esoteric Codes about SLNs and code art. But today I'm going to talk about another passion of mine, which is dithering. Back in the 1970s, they wanted to work out how to represent an image that has many colors using a small palette, such as black and white, for the pixels available on monitors of that era. Now, one approach would be simply to round each pixel to the nearest in-palette color. So the darker pixels would round to black in this example, and the brighter ones would round to white. But you can see how we lose a lot of detail that way. Dithering was developed to help you regain some of that detail. The flavor of dithering I'm going to talk about today is error diffusion dithering. For the first pixel, it works exactly the same way. You round towards black or white. But the amount that you round, like let's say we start with a pixel that's 60% black. If we round it the rest of the way to be a fully black pixel, then we've introduced an error of 40%. We take that 40% and we divide it among the pixels neighboring that one, and round them a little bit in the other direction. Then we evaluate the next pixel, and that one has already been shifted a little bit, and now its error gets distributed to the pixels around it. And that way the error gets distributed all around the image. Now, dithering doesn't have to be just to black and white. It can be to 16 colors or 256 colors, or actually to any arbitrary palette. And it's still widely used. It's just not as obvious with monitors that have tiny pixels and huge palettes of color. Now, there are many different dithering kernels that we can use. The kernels are the coefficient sets for that error distribution. The most commonly used one is called Floyd-Steinberg, and that's the one that Photoshop uses, although they have their own proprietary version of it. There's another one called Atkinson, which was invented by Bill Atkinson of HyperCard fame. And Atkinson is very good for keeping contrast in the midtones, but loses some detail in the darkest and lightest areas, because not all of the error is carried over. These kernels have not changed in decades. So I recently spent a week at the Recurse Center, virtually, and wrote a scoring algorithm to see which of the dithering patterns match best with the original image. And I do this by blurring both the dithered and undithered image, and then compare them using structural similarity index measure. To make sure I'm not introducing bias, I used one of the freely available data sets of faces from Creative Commons Flickr images, which I actually pared down myself with an emphasis on diversity. I also included some line art, which is difficult to dither well and trips up some of these dither kernels. I used a simple machine learning process, simulated annealing, to generate new dithering kernels to test. And I used both large and small versions of the images, starting with all the small ones to quickly weed out the ones that aren't going to work very well. It turns out of the random generated ones that I created, the most interesting were not the ones that were high testing, because they end up being very similar to what we already have, but are usually just more complicated. Actually, it was the medium to low testing ones, where the pattern of the dither interferes with the contents of the image, where things got more interesting. And here I have a series of images of the David, which I picked because it's so recognizable. And you can see in these examples, the noise and signal begin to merge, the dither encroaching into the subject matter. In addition to that, there are certain types of visual artifacts that are particularly distracting, such as vertical stripes. Here is an extreme case of this, where we have a kernel that has only one row. So no error is carried from one row to the next, and each one, it's as if it begins at the beginning again, which almost always causes these vertical stripe artifacts. But even without the artifacts, you can just have noise. I have a whole collection here of snowy David pictures. Dithers that drop some of that error, where not all of it is carried over to surrounding pixels, those lead to the high contrast images, like my collection here of goth Davids. So now that I had a test that scored kernels, I decided to bring it in a different direction. And I considered alternate computer histories. What if our screens had not been rectangular and did not have square configurations of pixels? What if we had triangular or hexagonal pixel configurations or other patterns? And I decided to focus on the equilateral triangle and to fake this out by creating triangular pixels that are 10 square pixels high. Then for each of those pixels, I get the average color. And from that, I dither it the same way I dithered the original square images and do the same comparison. So equilateral triangles are similar to squares in that each pixel has a neighbor in each of the cardinal directions. They have an up neighbor, down, right, and left. So we'd expect that the same kernels would test well. And it turns out that they do. Here's an image from the Flickr dataset and its triangular pixel version. And here is an image of me sanding that I used also for some of my tests. Pixelated, it looks like this. Here's a smaller pixelated version. And it turns out that the originals, like Floyd Steinberg, do pretty well. But they have some problems because the checkerboard pattern, which is very, very common in the original dither patterns, when you hit the 50% mark, this was actually something that Floyd and Steinberg and the other developers of these dither kernels wanted, that at 50% you would have a perfect checkerboard. The variation is Atkinson, where we also have a checkerboard, but it's larger. It's 2 by 2 pixels for each one. This works pretty well with square pixels, but with triangles, it creates sort of a flat-looking area, which is kind of distracting, the same way that the vertical stripes were distracting in the square pixels. So it turns out that my test actually picked up on this, and some of my randomly generated kernels actually tested better than Floyd Steinberg did in the triangular space. So I am actually still testing triangles, but I'm also underway creating the next shape, hexagons. But it turns out for hexagons, there actually is a place that we're already doing hexagonal dithering, and that's in the printer, because the printer layout of printer dots is actually a hexagonal pattern, and there actually are dithering kernels for that as well. So I'm doing this as part of a 10-year project called Dither Studies, where I dither not photographic images, but solid colors. And I dither them to palettes of complementary colors, opposite colors, to make the dithering artifacts as obvious as possible, as visible as possible. And this is something I've done through, I have a web app, I have videos and room-size installations of those videos. And more recently, over the last few years, I've created this series of paintings. But before I start actually painting triangular dithers, I want to find the triangular dither algorithms that actually work. So why study dithers? What's so fascinating about dithering? For me, the error diffusion dithering, it's a very simple algorithm. It uses nothing more than grade school math, and yet the patterns, when applied to solid colors, feel very irrational. To me, it's reminiscent of early computer art by people like Vera Molnar and Hiroshi Kawano, but really illustrate how little complexity it takes before logic feels irrational to us. It's a great illustration of that gulf between human intent and logic that occurs every time that we sit to write code. Thank you very much.
That was cool. Thank you, Daniel. I love the combination of, the very specific logic algorithm kind of thing, and then the, like, artistic, sort of how it feels to us after it's been fed through the algorithms.
Yeah, it was a really cool talk.
My cat. It's a catastrophe over here. By the way, I found out earlier today, today's O. Henry Pun-Off Day. So I don't know if you've ever heard of a competition where people just like fling puns at each other. But I found out apparently the annual ceremony event thing is always the third Friday of May. I just learned today. So
that is very cool. I'm sorry. Every time the cat appears, my mind is just jumping at, oh my God, cat.
He's a giant cat. Well, anyway, I think since I've been thinking on this, more puns are coming along. But anyway, I also thought hexagonal and triangular pixels were kind of an interesting visualization as well. I don't know. It was pretty cool. I appreciate this talk.
Yep. So, moving on from one cool talk to the next cool talk, again, on the theme of colorful pictures, our next talk is going to be It's a Picture, It's a Program, It's Piet by Anjana Vakil. Anjana suffers from a chronic case of curiosity. which led her from philosophy to English teaching to computational linguistics to software development. As a developer advocate at Observable, these days she codes and teaches from her home base in San Francisco. In the before times, you could find her speaking at events around the world. She loves to share the joy of programming and advocate for a more diverse, equitable, and ethical tech industry. Ask her about Recurse Center and Outreachy. She is an alumna of both.
Hello. Hi, folks. Hi. Oh my gosh, Bang Bang Con, so excited to be back. Well, I am so glad Pete has already come up a couple of times at the conference. I hope everybody is just as excited as I am to talk about Pete today. I'm Anjana Vakil. You can find me at Anjana Vakil on Twitter. And I'm really stoked to talk about Pete. So let's dive in. The slides are up on Observable, where I work as a developer advocate. And I am really stoked that I think a lot of people already are familiar with Pete, but I hope for the folks that are new that this will be illuminating. So Pete Mondrian might be a name that you recognize, but if you don't recognize the name, I'm pretty sure you recognize his art. So he was a Dutch painter famous for doing these very striking compositions, abstract paintings with large color blocks and lots of white space. And the question that we as intrepid programmers might be asking ourselves is, cool, art is nice, but what if we could run a piece of art like this as a program? So this is exactly the question that David Morgan Marr posed when he invented the programming language called Pete, named after Pete Mondrian. So Pete is an esoteric programming language, or ESOLang, or SOLang, depending how you pronounce it. I think a lot of folks are familiar with ESOLangs, but in case you're not, that's essentially a language that's not intended for practical programming and getting work done, but rather for joy and excitement and exploration and learning, and in many cases pushing the boundaries of our notions of computing and what programming even is. And so this is definitely the case for the language Pete, where we are going to treat abstract art as the source code for programs. What does that even mean? What does a program look like in Pete? Well, here are some examples. All of these are different ways that you can code a Hello World program in Pete. So all of these programs print the output Hello World to standard out. And this animated one has 3 different versions of ways you can color this program. So as you can see, they're all very colorful. They're made up of blocks of bright colors. And we're going to see how we can execute images like this as code thanks to the Pete interpreter. So how does Pete interpret these pixels, these pixel art pictures as programs? Well, it's all about colors. So as we saw, Pete programs are made up of bright colors, and this is the set of colors that can go into a Pete program. So we have the kind of rainbow colors, 6 rainbow colors here, a lighter version and darker version of each, and then white and black, which are kind of special colors, which we'll talk about in a moment. And so the idea is that in a Pete program, and here we've got a very simple little 10 by 10 pixel blown up program here. In a program, the blocks of a contiguous group of pixels of the same color represent a piece of data, so an integer value. And that is going to be the number of pixels making up that block. So in this case, we've got a magenta block here, and you'll notice it has some holes in it. There's some black areas and other colors inside of it, but all of these pixels make up a contiguous area that has 33 pixels. So this is going to be a magenta block of value 33. And then we have a dark magenta one here, which has 11 pixels, so 10 here and then one more. There's also a couple more 1 pixel blocks of dark magenta there, and so on and so forth for the different colors. Now, keep in mind, this is all about the contiguous series of blocks of pixels. So, for example, here we have 2 different dark cyan blocks, one that has value 5 and one that has value 1. They're separated by this white. Now, as I said, white and black are kind of special colors. White is is essentially like a void. It's like a filler. It's kind of empty space. And we're going to see what that means in a moment. And then black is essentially like a stop. It's also not a value, but it's more like the edge of the image. So essentially it's a no-go zone. We'll see what that means in a moment. All right, so the way a Pete program is interpreted is thanks to the help of something called a direction pointer. The way the direction pointer works is when we start execution of a program, the direction pointer starts out in the top left pixel of the image, and it starts out pointing right. And what it does is if it's in a color block area, it's going to try to move to the edge of that colored area, that same colored block, that is in the direction that it's pointing. So in this case, to the right. So here it's going to move from the top left corner 5 pixels over, or to the 5th pixel over. And this is the rightmost edge of this magenta block. Then it's going to try to move on from there into the next block. In this case, into this dark magenta one. And so on and so forth. Now here, I don't need to move to the edge of the dark magenta block that I'm in because it's only 1 pixel wide. So I'm already at the edge. So I can go into the dark cyan, go into the next one, eventually the green, and so on until I reach this light yellow block. Now here, the furthest edge in the direction the pointer is pointing is actually not here, but further down the image. It's going to be this lower rightmost pixel here. That's the furthest edge in the direction of pointing. So we jump down there, and now we've reached the edge of the image. So we can't go anywhere else, can't move on. So what the pointer does in that case is it turns 90 degrees clockwise. So it's going to start pointing down. And then it's going to move. Sorry, we just jumped ahead a little bit. It's going to move to the edge that's furthest in the down direction. It hits the edge again of the image. So it has to rotate once more. It's going to move again to the furthest edge. Now it's pointing left. So it's going to move that way, which is this block over here. Now it's run into black, which, as we said, operates sort of like the edge of an image. So it can't pass through the black area. It has to turn again and move to the next, the edge in the new direction, which is now up. So it's going to move back up to this top pixel here, which again is the edge of the image. It can't move on from there. So it turns again, but at this point it has done a full rotation in this light yellow block, and it hasn't been able to get out. So it's stuck. And that is how we tell a Pete program to stop executing. So this means the program is over and execution is finished. Now, we didn't look at this one, but the white pixels essentially are sort of empty space. So the pointer moves unhindered through any white pixels. Okay, so now how do we take this pointer movement and turn it into doing something? Well, it turns out that changes between one block of color and the next block of color, changes between those colors are actually corresponding to commands to the Pete interpreter. So the colors are arranged in 2 cycles. On the one hand, we have a hue cycle, which moves through the rainbow colors from red, yellow, green, cyan, blue to magenta, and then back to red, and goes on in that cycle. And this is called the hue cycle. We also have the lighter and darker versions of each color, and that makes up another cycle called the lightness cycle, where we go from light to normal to dark and back to light. So if we're, let's say, moving out of a light red block and moving into a dark magenta block, that difference in colors is going to represent 5 steps in the hue cycle and 2 steps in the light cycle. And the way that these steps work is the number of hue and lightness steps for a given color change corresponds to a command that the interpreter is going to run to actually do something. So in this case, if I were to go from light red to dark magenta, that's going to correspond to the out car command. And we're going to see what that means in a second. And keep in mind that these are not absolute, the color, like each color does not correspond to a particular command, but rather the difference between them is what creates a command. So if the color changes, if now I'm in a dark magenta block, then moving to the light red color would be a subtract command, or moving 1 step in the lightness cycle to light magenta would be a push, and 2 steps in the lightness cycle to regular magenta would be a pop. Okay, so moving fast through all of this, but we're not going to have time to look at all of these commands, but what do these commands do? Let's take a look at a couple. What they do is they tell the interpreter how to manipulate values on a stack. So a Pete program, it runs by means of a stack which has integer values onto it. And each command gives the program something to do with that stack. So for example, the push command says, okay, take the value, the number of pixels in the block of color that you just exited in that previous block, and push that value onto the stack. Then we have a pop command that says, take whatever's on top of the stack and throw it out, take it off and throw it away. There are some commands like add, which assumes that there are at least 2 values on the stack and says, take the top 2 values, remove them, add them together, and then push the sum as a new value onto the stack. There are also some more commands that have various operations, like duplicate, for example, is one where we read the top value on the stack, and then we push another copy of it to the top of the stack. We can also do input and output. So we can read from standard in with the in commands, and with out commands, we can take the top value on the stack and print it to standard out, interpreting it either as a number, because everything on the stack is going to be integer numbers, or we can take that integer and interpret it as a character code and print the character that it represents instead of the number. So you can check out the references in these slides for a link to David Morgenmar's description of all of these commands. Okay, so let's see how this works and try to run a program. Okay, so we have our little image here, our 10 by 10 image, and we know how our color commands work now, and we know how our pointer works. So let's put it all together. Okay, when I start execution, the pointer starts out in the top left, as we saw before. It's in the magenta block, which has a value of 33. It moves to the edge of that magenta block, so it's still in the same block, this magenta 33. Then, as we saw, it moves into the dark magenta. Now, that difference from the previous colored magenta to dark magenta, that's a lightness step of 1 and 0 steps in the hue cycle. That corresponds to the push command. So it takes the previous value, this 33, and pushes it onto the stack. So now we have something on our stack. Started out as empty. Okay, we keep moving into dark cyan. So now the difference between the dark magenta that we were in before and the dark cyan that we're in now corresponds to that duplicate command. So what we've done is we've taken with the previous topmost value, which was that 33, and created a new copy, put it on the stack. So now we have 2 33s on our stack. Then we're going to move into this green, where the difference between dark cyan and green, even though all these colors look totally different, the number of steps is going to be what corresponds to the next command we're going to do, and that is out as a character. So now what we've done, and let's just go back to see here, well, we took the topmost value, and when we moved into that green, that out command told us to print it as a character to standard out. And guess what character it made? An exclamation point. Oh my gosh, how unpredictable. And then we move into this light yellow, and that difference is actually going to be the same difference as we saw from dark cyan into green. So we get that same out command, and we print that last 33 that we had there as another exclamation point. Now we're in our light yellow block again, and we saw how that goes. We try to move, we have to turn, we try to move, we have to turn, and so on and so forth, until we realize that we're stuck. We've retraced our steps, gone in a complete circle in this same block, and we can't get out. So we exit the program, and we are done. Bang, bang. So, oh my gosh, we did it. We saw Pete run. Now, this was a really simple program, but you can do anything in Pete that you can do with a computer. You could write an interpreter for an entirely different isolang, for example, which Matthias Ernst did when he wrote a brainfuck interpreter in Pete. Like, oh my gosh. You could even Sergey Lewis developed an assembler to basically like compile to Pete and can create even more complex programs that way. This, what we're looking at, and it's very small here, but this is a text adventure game written in Pete. Amazing. So I think this is just like so cool that you can really force your mind to expand in terms of the notion of what is a program? What could execution be? How could the act of programming be more like the art of programming? And I just think that Pete is just such a great example of like bringing joy and excitement to programming. And so I am really happy that everyone has been excited about it. Thank you all for listening, and I have some resources for y'all in these slides, which you can find on observablehq.com/@Anjana/Pete-BangBangCon. So yeah, go check out the resources listed here to learn more about all of the details of Pete and see some other really awesome programs. There are some really great online tools, and interpreters, including an amazing web IDE called Masterpeats that Recurse Center alumna Gabrielle Sincadieu made, which you can play around and make Pete programs and try them out with an interactive debugger. So go forth, play with Pete, enjoy, and I hope it brings you lots of excitement, surprise, and joy. Thank you.
Thank you, Anjana, for that. That was great. I brought my own Pete program right here. I haven't ran it yet. I'm not quite sure what it does, but it does something. What do you do?
Sarah, I spent the whole time trying to come up with a pun to comment on the talk, but I feel I just won't. I will try better with the next talk.
I mean, coming up with a pun is like a good art. There's sometimes you just have to really kind of paint a vision in your mind to come up with it.
Oh my God.
That
was brilliant. I just want to give a shout out to Recurse Center. They have been supporting many Bang Bang Cons in the past and have some great resources. And many of our organizers are alumni of Recurse Center too.
Yeah, and I think Bang Bang Con even kind of spun out of some Recurse Center stuff. So, but you'll learn a little bit more about that tomorrow as we wrap up our session. But thank you for that. I love esoteric languages. It's fun to see what people decide is such a zany idea that they're going to try and make work as an actual programming language anyway. So,
and I just love the idea of making a text-based adventure in this graphical language. Right, it's flipping what a game is.
It flips what you expect. Exactly. Yeah, I love it. So thank you for that talk. That was great. Our next talk is a little bit more of a performance, I believe, than a talk. But our next speaker likes to learn by drawing things. They work on all things infrastructure and have a soft spot for data stores and metrics. Outside of tech, our next speaker tirelessly covers everything in yarn and plays ukulele, which you'll get to see a little bit of. You may have also seen our next speaker off and on throughout the course of our conference. So Alicia Rushkovska is our next speaker, and take it away.
Hi, everyone. Long time no see. So as you heard from the intro, I really, really like databases and data stores. And one of the things that I find helpful in my daily job as a DevOps/SRE, whatever you call it, is imagining those elements and infrastructure that I'm taking care of as little characters, because then I can communicate with them and I can care about them and I can actually think about their journey. And I wanted to share that journey of a little database with you today. Before we dig into it, I wanted to present our hero and other personas that are going to appear in this talk, partially because I think it's cute, but also because my drawings are maybe not that great, so you might not be able to recognize them. So the little database is now our main hero on the journey. It's working with the app, who is evolving and growing, and it's getting some replicas. It's being orchestrated to help out with the increased growth and traffic coming from the app. And it also gets to meet proxy SQL, because at some point, it's just not enough to have replicas. So join me on the journey. The lone hero. In not so far and distant land, an app prepares to handle brand new traffic for the brand new day. It's Monday morning. Who can say, how many users will there be? App is impatient to wait and see. The first login request comes in. Username, password, all within a call to backend API. Now app can try to verify if the connection can be placed. Sends to the little database. The database opens one eye. A new request comes through the wire. Excited, reads the message quick. The SQL query does the trick. It sends a response right away. The user cannot start their day. As morning travels coast to coast, the app has more and more to post. The DB works with all its might, ensuring very acid writes, while latency is kept down low so app can work with even flow. It indexes its every table to make sure that it is able to answer any query quick. A B-tree is a neat new trick it learned from theory of graphs. It goes ahead and always grabs primary index for its store, then uses it to compare the whole table space, traversing through only the most relevant of roots. It also tries to use the RAM to make sure it can quickly scan the most popular of the requests. Whenever then the app in quest with a repeated query pattern, it can response get from the buffer instead of reading from the disk. It's how it keeps itself so brisk. As day goes by, the buffer pool gets significantly less cool, decreasing miss rates as it goes, improving speed of data stores. Suddenly, the traffic spikes. The app has gotten many likes and shares from influential folk. Now, many people want to poke and use the app in their new flow. Things are starting to get slow. The database can barely run the queries coming in. It's slammed. As app is scaling to respond, 2 new instances get spawned, more connections are flowing in. The little DB strives to breathe. And in despair, it tries to cram all the new threads into its RAM. Alas, the instance type it's on only has so much RAM in store. A new connection comes and dooms our little hero to an They crash. As app is trying to serve its pages, it seems like it is taking ages. What's the cause of this delay? Database server has gone away. The app starts sending 105s, waiting for data store to come online. The DB was able to reboot. It seems the failure was pretty acute. Alas, what is this odd exception? It can't handle a write connection. It seems that after the reboot, any writes are kind of moot. The app throws errors left and right. The user stuck without the write. DB remembers back in the day, it has decided on a way to secure its data stash after a very sudden crash, and to have some time to check that there isn't any wreck. It sets read-only on its store. Now it just needs to restore the proper config in its place. The app no longer sees the trace. Finally, it can do some writes. It's gonna be slow as it tries to handle all the DLH jobs. After a failure, the coming gobs. All the reports to generate, all the subscriptions to activate, all the indexing to dissipate, all the values to calculate. Everything has to propagate to make up for the time the app had to wait. Once all the jobs have been handled, now it has time to finally untangle how to make sure the app can connect, even when DB is currently wrecked. It looks in the mirror as it ponders and sighs. What could it do if it suddenly tries to answer too many requests all at once, ensuring that none of them bounce? It would need a way to be still able to see what is happening and react to it too. Is there maybe a way it could start to be 2? If one instance drops, the other steps in. How could it get a hold of a twin? Mirror, mirror on the wall. Can I make myself a clone? It would need to be able to have config of mine, but that's all in the source code, so it should be just fine. We can spin up an instance, allocate all the RAM, make sure that it is ready for the bad if I'm jammed. And then every time I write something in store, it should always transcribe it word for word, like it's lore. It spins up to a new host with its configuration. Now all that is left is to set up replication, creating a user and password for each, so they can both primary easily reach and get access to bin logs or GTIDs, replicating everything little database did. It also wants to make sure failovers work to ensure that the app can get a network connection to a writable store. Orchestrator could help with this chore, monitoring all instances, making sure that a host can handle connections if the primary is toast. It adds a new host into its VPC. Now Orchestrator is all set up to see how the DB is doing and reacting to queries. How much is replication lagging behind primary? Is there a need for a replica to come up to speed? Now that failovers work automatically, the database is dramatically less worried about its resilience. Very proud of its brilliance, it looks forward to a traffic spike. Now it's unstoppable, feels like. But the traffic comes and soars, growing strong and needing more and more connections from DB. Failovers work, yet it must decree it's not enough to keep reacting. It must become more proactive. Even more growth. As the user base of apps still grows, it seems that more and more inflows are coming through from every angle. While database can mostly handle connections that are flowing in and always fail over back to a twin, it seems that it's just not enough. When traffic spikes, things still get rough. it starts to ponder about resources. Could it potentially limit the sources of traffic to the data store? With the same assets serve more connections and not topple over? Can the user needs easily cover? The reads could all probably go to replicas, like is kept so low, and then the writes what vary of has to be only the primary. The connections can probably also be shared without the user experience impaired. It needs to find a wise new friend to whom the app can always send requests and let that friend decide how is it going to then guide them to the database using multiplexing without a need for refusing any connections from the app. Who has the skills to bridge this gap? Orchestrator raises a hand. It has a wise and helpful friend. Proxy SQL can join the crew to handle connections and multiplex too, assigning the replicas to a reader group, allowing the database to recoup resources for writing to the store, enabling the cluster to handle more requests and send responses quick. Add to it the multiplexing trick, and now the app can grow and grow without the DB getting slow. Epilogue. Everything is running smoothly. The database is absolutely thrilled with how well it responds. The traffic spikes no longer spawn countless threads, eating up all the RAM. Now it's time to have some fun. Oh joy! The app just got a new deploy. New features for users to enjoy. Can't wait to get a sort of data. It's a glimpse of it from beta testing of the all new flows. It seems they come up with only pros. Alas, something's amiss. No requests coming. Deploy is misconfigured, and the app has crashed. The DB threads are being slashed. Where are all the connections? Database has no directions. It tries to calm down and not feel bad. Surely the app is coming back. Long seconds pass and silence looms. Nothing can stop the impending doom. Saddened, it plops itself on the ground and then meekly looks around, trying hard not to give in to sadness and crack. It starts singing a song for the app to come back. It starts singing a song for the app to come back? It starts singing a song for the app to come back. Do you want to store some data? Come on, let's add some in. You never asked me anymore. Please start some more. Let it win. We used to be best buddies, and now we're not. I wish you could tell me why. Do you want to store some data? Doesn't have to be your data. Okay, bye. Do you want to store some data? Doesn't have to be a lot. Your queries are long overdue. My buffer pages are no longer even hot. It gets a little lonely, all this idle room, just watching the hours tick by. Do you want to store some data? Doesn't have to be your data. Please, I know you're out there. Proxy's asking where you've been. They say be ready, and I'm trying to. I'm right here for you. Send queries in. We only have each other. It's just you and me. What are you gonna store? Do you wanna store some data?
That was delightful. That was wonderful. That was everything I hoped it would be out of that talk.
That was a wonderful talk. The tune is still stuck in my head.
Yeah. And, it dragged us all on an emotional journey, I think. And I definitely saw that in Discord. The
What
empathy
a
of
roller
everybody
coaster
that
of
was,
emotions.
yeah, everybody just loved it. It was wonderful. I don't even have a good pun for that. It was just
We were all
lovely.
rooting for the little database.
Yes, definitely. And I'm glad in the end, the little database definitely pulled through. So thank you for that, Alicia. That was wonderful. Would you like to bring us into our next talk?
Sure. So our next talk is about making music in Emacs. The next talk is by Zachary Canfer. Zachary spends a lot of time coding Lisp, playing guitars, and doing improv. He runs Emacs NYC and recently got into hats. You can find him at zck.org.
Hi, I'm Zachary Canfer, and this is Making Music in Emacs. So over quarantine, I've been bored at home, and I found this Android app called Anti-Stress with a bunch of mini games and activities. One of which is a way to make some music, some digital music. And it's pretty cool, but kind of as with a lot of things, I want more features than the original app has. So I thought about it and I said, well, I'm a programmer. I could make something like this. I just need to build it on a system that has a lot of flexibility and customizability. And when I think about that kind of system, I think about Emacs. Now, Emacs is a text editor with a history going all the way back to the 70s. And it's super customizable. One of the coolest things about it is the language that they use to build Emacs is the same language that you can use to extend it. So anything they can do, the developers can do, you can also do. So I looked into the features that Emacs has, and it actually turns out that it can play sounds. And at least the way it plays sounds is with something called wave files. But what are wave files? So I searched the internet a little bit, and turns out that wave is just a musical file format. Or as I came to learn, it's kind of an annoying file format. And here's why. So numbers can either be one byte numbers can be unsigned, but if you have a 2-byte number, it's actually a signed integer, which is inconsistent. And it's little endian by default. You can switch it to big endian, but if you do that, Emacs can't play it. So little endian it is, which I just find confusing to think about. And there's duplicate data fields. So here are 3 fields those make sense. But then we have another field, block align, that you just multiply a couple of the other fields together. So it's entirely a combination of those other fields. But you need to have it or it's not a wave file. And even more so, there's this other field that is just you multiply 3 of them together. So you can entirely calculate that, but you have to do it and put it in the file. So the last part of the file, the biggest part of the file, is data. Or as one website that I found described it, the actual sound data. Now, what is data? And I looked more, I found some more descriptions of it, and it turns out that sound is a wave, it's a waveform, and if you just measure the height of that waveform, that's what the data is. So this sample one, it starts at 8, goes 9, 11, 13, 14, 15, then back down. If you just put those numbers in the file, that's all the data is. So great, now we can write a wave file. So let me demo ZMusic. So the highlighted blue row is a beat. And if we start playing, you see it's going to go down and it's going to wrap. And you can use the mouse to add some notes. And you can see we can have beats with multiple notes on it. That's fine to do also. So this is a really simple ZMusic, but that's fine. So some other features that I didn't have time to demo, you can have different scales. What we used is the minor pentatonic, which I picked because basically every note sounds good with every other note. That's not the case for most other scales. But if you want to, you can swap out for a minor scale, a major scale, any other scale you want. You can also save your music to a file. And the interesting part here is that I had to make silent notes. Normally, if there's no notes on a beat, we just don't play anything for that time step. But if we're writing to a file, we have to put some data there to say, don't make any noise during this time period. And I also have terrible sounding keyboard support. You'll see why later. Here's some things I learned about Emacs. So, spacing issues. So those things I was clicking on, those dashes in the beat, those are buttons in Emacs. And because of the way Emacs buttons work, you can't put two right next to each other. There has to be a character between them. Now, you could put a space between them, which would work, but then I found you might accidentally click on the space when, especially if you're trying to go quickly. So I looked into Unicode to see if there's any characters that I could put there that maybe wouldn't be as big. I found something called a zero with space, which is great. So I can put that character as not part of the either button in the middle, but it won't take up any space, so you won't accidentally click on it. But interestingly, this zero with space in Emacs has width. So we're just going to insert a greater than symbol, 200 zero width spaces, and then a less than symbol. And if it really had zero width, those two, the greater than and less than symbols would be right up against each other. But we see that here they actually have width. And what's happening is, I think what's happening is the character itself has zero width, but between each set of characters, Emacs reserves 1 pixel of width for the cursor. It's hard to see, but there's a line flashing there. That's the cursor between two zero width spaces, I think. But it's still pretty close to zero width. So the first couple ways I tried to play sound don't actually work. So like we were talking about before, Emacs can play sound, can play these WAV files, but it blocks while it's playing them, which is not great if you want to do things like add other notes while it's playing or even pause it. Emacs does have asynchronous ways of coding, but if you do that, it doesn't make any noise, and I don't actually know why. So the way I went with that works is you just take that wave data and you write it to disk, and then you shell out to the native wave player on your operating system. And that works as long as you only do it once at a time. Because if you have multiple, if you call that multiple times at the same time, if they're overlapping, you'll get really weird interference. And that's why the keyboard from before doesn't work well. So here's the one thing I learned about music theory. Music theory is not easy to program with. When I was looking for some concepts to program with, I found scale degrees. But you don't want to program with scale degrees. So if we look, this is a low C, and then, so that's the first, the second of the scale, all the way up. This is the next C, it's a C an octave up, and that's also a first. So with scale degrees by themselves, you can't really differentiate between that, which isn't great if you want to have at least an octave. So then I found intervals, and it turns out you don't want to really program with the intervals either. It does solve some of the problems. So we see over here, the octave is 8, so that works. But you see we have like a major third or a minor third. So there's this extra data you have to kind of keep along with it. You can't just say a third. So I thought about it, music's really frequencies. So at a low level, we're just going to say like an A, like a concert A is just 440 hertz. And that's what we're going to use at the really low level. The level that humans are going to use, I'm going to say there's a root note. And then we're just going to say how many semitones up from that root note you are. And then we're just between that and the low level, we're just going to transfer those to frequencies and use them, and it's going to work fine. So that's pretty much it. I have notes references and source code at zck.org/bangbangcon2021. I'm a co-organizer of emacsnyc.org. And feel free to email me. And I think we have about a little over a minute, so let's do some more music. One of the cool things is as you're building it up, the music kind of becomes more layered, and so it sounds like a more complicated song than it is just based on the music at any one time. You'll see what I mean. Thank you.
Oh my gosh. There's so much about this talk that I just absolutely love. First is that not only is it like making music in Emacs, but the whole thing was done in Emacs, the whole presentation, and the whole thing was live. I love that. But also, I don't know if anybody brought this up on Discord, but Mirabai, our captioner, was also captioning the music. And it's absolutely wonderful. So, oh, thanks, Kat. This talk
Yeah,
was great.
it was a great talk, and I love how musical Bang Bang Con has become over time. Um, I think all the talks that we saw today were what Bang Bang Con is. They were colorful. They were about art. They were about music. They were about joy, surprise, excitement of computing.
Yeah, definitely. And there's not a lot of conferences that would take talks like these. Just they're so almost like so far out there from your typical tech talks that you assume that really Bang Bang Con's kind of the only place you can appreciate like a whole night full of just musical and fun and artistic talks. So yeah. My cat is whacking the space bar with her tail. So just I'm hoping it just doesn't erase part of our notes that we have to talk about. All right, so we're getting close to 9 o'clock Eastern, which means it's about time to wrap up, and it's about time for our hallway track. So if you're watching live, we have a hallway track on Skittish coming up next. If you're watching on SyncWatch, there's not a hallway track after this. Our next live session 9, will come right after this. So you can tune into that if you're watching. Thanks to all of our speakers again. You all were great. This is a wonderful night. And thanks to all of our sponsors again for helping make Bang Bang Con an absolutely just wonderful, a wonderful conference.
Yeah, we had a great slate of talks today. And we will see you again when the Sync Watch happens for these talks.
Yeah. So the next live stream happens at 10:30 p.m. IST, 7 p.m. CEST, 6 p.m. BST, 1 p.m. EDT, and 10 a.m. PDT. And then the next Sync Watch this session will be 8 p.m. or 9:30 p.m. Sorry, IST, 6 p.m. CEST, 5 p.m. BST, 12 p.m. EDT, and 9 p.m. PDT. I'm sorry to our captioner that had to try and actually write all that out.
Yeah, and thank you for watching Bang Bang Con. Thank you for staying with us. Please tweet with hashtag virtual Bang Bang Con. We have the Discord open. You can talk to the speakers. You can tweet at them. You can appreciate the just the amazing talks that we had today and talk to them. It will really make their day.
Yeah. And hopefully see you on the hallway track if you're live, or hopefully see you in the next session if you're watching this on SyncWatch. Have a good day.
Bye.